Is OLS regression truly a data science and machine learning algorithm? A critical examination. Aloha. In the increasingly broad domain of data science and machine learning, DSML, many traditional statistical tools are often retroactively labeled as DSML algorithms. Among these, ordinary least squares, OLS, regression is frequently included in DSML curricula, textbooks, and software libraries. However, a closer philosophical and technical examination raises a compelling question: is classical OLS regression truly a machine learning method? This video explores that debate, drawing attention to the conceptual foundations of machine learning, and ultimately argues that while enhanced forms of regression modeling may qualify, the classical one-shot OLS procedure falls short of the defining characteristics of machine learning. To begin with, it's crucial to recognize that OLS regression is not a product of the machine learning era. In fact, the least squares criterion, the foundational principle behind OLS, was first introduced by Adrien-Marie Legendre in 1805. That's over 2 centuries ago, long before the invention of computers, the internet, or anything resembling modern data science. OLS was developed in the context of celestial mechanics, not big data or predictive analytics. The method has persisted through centuries due to its mathematical elegance and interpretability, but this longevity can also be misleading. It reinforces the notion that OLS is a cornerstone of data analysis, yet its age highlights a key limitation: it was never designed for the scale, complexity, and adaptive needs of contemporary machine learning problems. To illustrate the crux of this issue, consider the following metaphor. Suppose an employee is assigned a task by their boss. The employee completes it and submits the result in 1 hour. The boss, noticing issues, attempts to provide feedback with the intent of helping the employee improve. However, the employee walks away without listening, does not make revisions, and thus, learns nothing from the experience. This scenario mirrors classical OLS regression. The model is fit once, it generates results, but it does not incorporate feedback from its errors to refine itself. If we accept that learning implies the ability to adapt based on feedback, to update performance through iterative correction, then clearly, no such learning has occurred in this one-shot process. The metaphor reveals a core tension: learning involves interaction, adjustment, and responsiveness, none of which are inherent to the classical OLS framework. The key difference between classical statistics and DSML lies in the iterative nature of learning. Modern machine learning algorithms, from gradient boosting to neural networks, involve continuous improvement cycles. These models make predictions, evaluate errors, and adjust parameters accordingly, often over many epochs or iterations. Learning occurs because the model reflects on its mistakes and improves over time. In contrast, OLS regression solves for a set of coefficients in a single optimization step. This closed-form solution does not update based on residuals after estimation. While analysts may refit the model manually using new features or transformations, this activity occurs outside the algorithm itself. The model does not learn in the algorithmic sense, it simply fits. Put it bluntly, optimization per se is not learning. This disconnect becomes even more apparent when classical regression variants are applied naively to modern data. A notable example is stepwise regression, a variable selection procedure often used with OLS. In this method, predictors are added or removed based on statistical criteria such as p-values or adjusted R-squared. While once popular, stepwise regression is now widely criticized, especially in the context of high-dimensional or large-scale data. Notably, economist Gary Smith warns researchers to step away from stepwise regression, arguing that the procedure is not only statistically fragile but also poorly suited for big data analytics. The method tends to overfit, produces unstable models, and can inflate type 1 error rates. Its reliance on statistical significance thresholds makes it vulnerable to spurious correlations, a fatal flaw when dealing with datasets containing thousands of variables. In this light, Stepwise regression represents a classic example of how older OLS-based techniques do not scale well and may even mislead analysts working in modern data environments. From a methodological standpoint, OLS regression is fundamentally model-driven. It relies on strong parametric assumptions, linearity, homoscedasticity, no multicollinearity, normally distributed residuals, random residuals, and independence of observations. These assumptions are not just background conditions, they are central to the validity of the model. In contrast, machine learning methods are often assumption-light or assumption-free, letting data patterns dictate model structure. This contrast underscores a philosophical difference. Classical OLS begins with a rigid framework imposed on the data, whereas machine learning begins with the data and learns structure through repeated feedback. Further, classical regression is primarily inferential. It provides coefficient estimates, p-values, confidence intervals, and a framework for hypothesis testing. The emphasis is on interpretability and statistical significance, not on predictive power or pattern discovery. Machine learning, by contrast, is fundamentally predictive. It seeks to minimize error on unseen data, often at the cost of interpretability. Thus, while regression and machine learning can both be used on the same data, their purposes, explanation versus prediction, diverge. That said, it would be an oversimplification to entirely exclude all regression models from the machine learning landscape. Many modern enhancements to regression modeling introduce learning-like characteristics. For instance, ordinary least squares can be fit using stochastic gradient descent, SGD, an iterative optimization algorithm widely used in machine learning. In this formulation, the model updates its weights based on small batches of data, progressively minimizing error, a clear learning process. Additionally, penalized regression methods such as ridge regression, lasso, and elastic net incorporate regularization terms that guide the learning path, helping the model generalize better to new data. These techniques not only improve performance but also bring regression into closer alignment with machine learning objectives. Further still, online learning and ensemble techniques embed simple linear models into complex adaptive systems. In online learning, models update their coefficients one observation at a time, refining predictions continuously. Ensemble methods like boosting chain together weak learners such as linear regressors, where each model is trained to correct the errors of the previous one. In such contexts, even a humble linear model participates in a broader system that does, in fact, learn. Nonetheless, between linear regression models and decision stumps, which are shallow decision trees, decision stumps are overwhelmingly more commonly used as weak learners in ensemble methods, particularly in boosting algorithms. In conclusion, while traditional OLS regression is not a machine learning algorithm in the behavioral sense, it neither adapts nor learns from its errors. Enhanced regression models that incorporate iterative optimization, penalization, or online feedback mechanisms clearly do fall within the scope of machine learning. The distinction is not merely semantic but reflects deep differences in goals, assumptions, and algorithmic behavior. So, we can reasonably assert that classical OLS regression is not machine learning, but modernized, feedback-driven regression models can be. Recognizing this nuance helps clarify the boundary between statistical modeling and machine learning, a boundary that continues to evolve as both fields converge in the era of data-driven science. So, what's your take? Should we still classify linear regression under the category of data science and machine learning, place it in a gray area between classical statistics and DSML, or exclude it from DSML altogether? I'd love to hear your input. Please leave a comment. And if you found this thought-provoking, feel free to share, like, or subscribe. Let's keep the conversation going.